You'll be using the Metropolis Hastings sampler that we built yesterday. There's a .py file that's in the GitHub repo. In the general channel for the Slack is instructions on how you can import that, so you can use the MH sampler we built yesterday. One short note, I said to just do from DSFP MHMCMC import star. Generally speaking, that's a bad idea. Just don't import star. If you're curious about it, ask me about it, but I won't take everyone else's time to explain that right now. Thanks. All right, we're approaching our lunch break here, so I think we'll take a moment now. If I could just get everybody's attention up towards the front. Megan's going to walk us all through the solutions to the notebook. Okay.
All right. Okay, so I'm running this in Google Colab, which is a very shiny tool I discovered recently and use for everything. Which does, I found out, lead to some issues with like indentation syntax with Jupyter Lab. So I apologize if you were getting like red things. But anyway, I'll just go through quickly some solutions. I don't guarantee that I got like the best possible solutions to these problems because, as you probably learned, these MCMC can be really sensitive to exactly where you start it and exactly what your sort of step size or covariance scaling on the sampler is. But I think I got some decent results. So we're loading up this data set for HD209458b, which if you read the text, you'll know was the first transiting exoplanet to be found and was discovered 20 years ago yesterday. So it seemed like a fitting thing. So if we just take a little look at the data, this is useful to plot because you can see that it's not a super long period planet. You don't see like really coherent curvature or anything. And B, you can get some sense of the amplitude of the signal here, which is going to come in handy in a second. So we're going to write this sinusoid function. And for my prior, I set up, the only physical constraint I used was that the amplitude of a sine wave is not negative. So I gave it a lower bound of 0 in the amplitude. Everything else, I kind of eyeballed the data and said, it's not really obvious what the right answer should be for either the T0 or the RV0. So I'm just going to say that they're somewhere within this extremely broad range, many of which are not actually plausible solutions, but we'll just give it a big flat prior. And same with amplitude, it can go up to way higher than what the data actually indicate, but I wanted to avoid using the data too much in the prior. You could be a little more conservative than this in your prior. Yep. So I chose these initialization values. Again, I didn't really put any effort into figuring out what T0 and RV0 should be. I just guessed an amplitude that looked like the semi-amplitude of the data set, which is okay for this particular application. So we're going to run this, and it'll take a little while. Okay. So this is what I get, which is red stars initialization. And you can see that we're sort of wandering off to a different region of parameter space. And I made each of the points somewhat transparent. So the fact that these blue points are opaque means that we're sitting at each of these possible solutions for a while. So this is not ideal. So we're going to do the SciPy optimize minimize. And for that, I wrote this NLL, negative log likelihood function that is literally just negative of the log likelihood. So this is something that we can minimize to maximize the likelihood. We're going to run through an optimization here and take a little look at this, and it looks good. Here is the phased version. So I just did mod of the best fit orbital period here and overplotted the model, and that looks like it's fitting pretty well. So now we know that we're initializing the MCMC in the right place. If we try it again, this time it looks better because we're not wandering off to one corner of the plot and staying there, but it's still staying on each of the points for quite a while. So next, we can look at, we can see that in another way by looking at the trace of any of the parameters, which is showing that they sit on a certain value for a while. We can calculate the autocorrelation function, and this should show something kind of funky that has a lot of power at long lag times. So that, again, is another way of showing that you have to go a really long way, a long number of samples before you get to an independent draw. And it's calculated as something like 300 samples, although can't necessarily trust this this guess because there are not that many independent samples in this chain at all. Okay, so what I did here is I just decreased the step size by an order of magnitude on the period parameter, and that ended up pretty much solving this issue. So now we can see that we're no longer resting on any given point for a while. And if we look at the autocorrelation function, it just really plummets after a few steps, meaning that you don't have to go very far in terms of the lag in order to get independent samples. This is calculated as 17 for my case. So the fact that you have to go 17-ish steps to get an independent sample means that you want to go like several hundred, 2,000. You might also want to go several 100,000 steps times the correlation length to get the steps. So I just ran this for a while and plot the outcome, and we are finally getting a nice PDF here. And along the way, I didn't do all of the diagnostic plots at every step, but if you wanted to, you could put in these pairs plots and the traces and things and see that the behavior is improving in many ways. So this is now a nice PDF, and we can integrate it up to answer these questions about the underlying probability of different values of the parameters. I will give the caveat that we're not efficiently sampling all of parameter space. So asking about the probability that K is greater than 90 here, we never actually got samples that went up to 90. And so this isn't necessarily like, we do have some information that 90 isn't very likely, but we would have to do a more in-depth sampling around that region in order to actually get a super believable answer to this particular question. Okay, so I don't know if anyone got to problem 2. As you noticed, it takes a lot of time to fiddle around with things in order to get your MCMC working. And I apologize for frustrating you, but that is kind of part of the goal of the exercise, is to learn that it's really hard to actually like trust the results of your MCMC, and there should be quite a few things that you should check in order, because there are many ways that you can go wrong with the samples that you're getting out. But to give you a little look at this, so the next thing that is in the notebook is to pick a different star. This is a star with a very eccentric planet. So this one has a period of about 100 days. If I phase it up to that, it looks like this. So we can no longer use a sine wave. Now we have to put in a Keplerian. And so I gave you some functions in the notebook to get model predictions for a Keplerian orbit. And now we've increased the number of free parameters, and we've added some free parameters that are a little tricky to sample. So we now have eccentricity and an angle, the argument of periastron, that tells you what phase of the orbit is the passage closest to the star happening. And so these two parameters are very highly correlated with each other. They're also, omega is especially hard to sample because it is an angle. And when we write the priors, which we'll do down here, um, there is a physical prior on omega, which is that it should be between 0 and 2 pi or between negative pi and pi. But we know that it should kind of wrap around from that, and it's hard to give a flat prior that does that. So for that reason, we're going to have pretty inefficient sampling in this chain because we'll end up being like trapped near one edge of the prior without the ability to flip over around to the other edge the way that we might like to. So for a couple of reasons, this is going to be an even more inefficient way of doing things. So here I just kind of fit by eye a little bit some good starting parameters for this. And I tried running naively, and you can see that there are really long correlation lengths here. And we don't even have enough independent samples to make a good corner plot. But you can see that there are strong correlations between many different things just from the few points that you have. So finally, we can reparameterize this. There's a paper that suggests changing eccentricity and omega to be E cosine omega and E sine omega as the two free parameters. And this gets rid of some of the covariance, and it also gets rid of this discontinuous issue with the angle. So if we change that and rerun it, we actually get pretty nice behavior. And we're able to get, again, I didn't run this for long enough to get really beautiful corner plots because it would take a while. But we can start to see that we are getting decent constraints on things. And that was the end of the exercises.